The nearest star is not a place, it is a direction. You can point to it and travel toward it for the whole of your life and the lives of everyone who comes after you and never once arrive. It is called Proxima Centauri, and it sits just over 4 light-years away, which is 40 trillion kilometers, close enough that we have already found a world about the size of the Earth circling it. The fastest thing our species has ever built would take 73,000 years to reach it. Light itself takes more than 4 years, and light never slows down. But distance, it turns out, is the least of it. Because when you follow the journey to that nearest star all the way through, honestly, step by step, you find that arrival keeps slipping out of reach, and the closer you look, the further off it moves. By the end of tonight, you will understand exactly why the journey to the nearest star is scarier than you think, and why, in the truest sense, you never arrive. Get comfortable and let yourself sink in. If you enjoy having something you always assumed was simple, quietly taken apart until it turns strange, a slow like and a subscribe help this channel reach more curious minds like you. Because by the end of this, the nearest star will stop feeling like a place we have not visited yet, and start feeling like a direction we can only ever fall toward. Now, let us slowly settle into the dark. There is a star you could point to tonight, if you knew exactly where to look, that is closer to us than any other star in the sky. It does not look like much. You cannot actually see it with your eyes, even on the clearest, darkest night, from the emptiest field on the planet. It is a small, cool, red thing, quiet and dim, and it hangs out there in the southern sky at a distance of just over 4 light-years. In the language we usually use for space, that makes it our neighbour. It is the nearest doorway out of our own solar system, the first stop on any map of where humanity might one day go. And tonight, slowly and carefully, we are going to try to reach it. I want to tell you its name, because you will be living with it for the next while in the dark as you drift. The system is called Alpha Centauri, and it is not 1 star but 3. 2 of them, Alpha Centauri A and B, are a pair of suns rather like our own, circling each other out there at a distance of about 4.37 light-years. The third is smaller and stranger, and right now a little closer than the other 2. It is a red dwarf called Proxima Centauri, and its name simply means the nearest one. It sits about 4.24 light-years away, which comes out to something close to 40 trillion kilometers, or about 25 trillion miles. It orbits the other 2 suns so far out and so slowly that a single loop around them takes it something like 550,000 years. Proxima is not a smaller copy of our sun. It is a dim red ember, with only about 12% of the sun's mass and about 14% of its width, glowing at a surface temperature of roughly 3000 Kelvin, which is cool as stars go. It is so faint that even though it is the closest star to us in the entire universe, apart from our own, you would need a good telescope to find it at all. And yet, circling that little red ember, there is a world. In the year 2016, astronomers announced that Proxima has at least 1 planet close to the mass of the Earth, moving around it in a tight, fast orbit. They called it Proxima b. It is roughly the weight of our own world, and it sits at just the right distance from that dim star to be, in principle, the kind of place where liquid water could exist. On paper, in the driest technical language, it is a potentially habitable planet around the nearest star to the Sun. Let me try to make that distance real for you, because 40 trillion kilometers is a number that slides right off the mind, and it is meant to. Numbers that large stop meaning anything. They just register as big, and then the feeling fades. So let us shrink the whole thing down to something you can hold. Imagine the sun is a basketball sitting on the ground in front of you. On that scale, the Earth is a tiny grain of sand, about the size of a grain of salt, rolling around the basketball at a distance of roughly 25 meters, most of a soccer field away. Everything you have ever known, every person who has ever lived, every ocean and mountain and war and love story in all of history, all of it happens on that 1 grain of salt, 25 meters from the basketball. Now on that same scale, where is the nearest star? Where is Proxima? It is another dim little marble, and it sits about 6,500 kilometers away. Not 6,500 meters. Kilometers. If the sun is a basketball in your town, the nearest star is a marble on another continent, an ocean away, with nothing in between but empty floor. Sit with that picture for a moment as you lie there. Between the basketball and that far-off marble there is nothing. No other balls, no grains, no dust you could see. Just floor, thousands of kilometers of empty floor in every direction. That is the true texture of the space between us and the nearest star. It is not the crowded, glittering starfield you see in pictures, with suns packed shoulder to shoulder. It is the emptiest thing there is, a gap so large that the fastest thing we have ever built would need longer than the entire history of our species to cross it. And that marble on the far side of the world is the closest one. Every other star is further. This is the near neighbour, the easy trip, the short walk, and it is already almost beyond imagining. So here is the situation we begin with tonight. There is a real destination. It is not a fantasy, not a smudge on a photograph, not a maybe. It is a mapped star with a mapped world in what we call the habitable zone, and it is the closest one there is. Every ingredient you would want for a story about humanity finally leaving home and arriving somewhere new is sitting right there, 4 light years away, waiting. If we were ever going to go to the stars, this is the star we would go to. This is the one. And that is exactly why the story we're about to tell is so quietly unsettling. Because the closer you look at the journey to that nearest star, the more you start to notice something strange about it. The problem is not really that Proxima is far. We're going to talk about how far it is, and the number is worse than most people expect, but distance turns out to be the least of it. The harder problem is that when you follow the physics of the crossing all the way through, honestly, step by step, you find that arrival itself keeps slipping away from you. Not because the star moves, because the act of getting there, of actually stopping at that world and standing on it, runs into one barrier after another, and each barrier is a different kind of impossible. Tonight I want to walk you into that slowly. I want to treat the nearest star not as a place on a map, but as a direction, a way of pointing, and I want us to travel in that direction together, one careful step at a time, and to notice what happens at each step. Because what happens is that the arrival we are travelling toward keeps receding. It stays 4 years of light away in the simplest sense, but in every sense that matters to a living traveller, it moves further off the harder we try. By the end of tonight, you're going to understand something that sounds like a riddle and turns out to be a fact. You can aim your whole civilization at the nearest star and build the finest ship anyone has ever imagined, and point it perfectly and launch it, and still, in the truest way, you never arrive. I know that sounds like a contradiction, that you could aim so carefully and travel so far and still never arrive, and for most of this night it will feel like one. But it is not a contradiction. It is the honest result of following the physics all the way to the end instead of stopping at the pretty part. And the strange thing is that the answer is not really hidden in the far reaches of the cosmos. It is hidden in plain sight, in the numbers we already know, in the way speed and time and matter and even our own reasoning behave, all of it sitting right here in front of us, waiting to be looked at slowly. So that is what we're going to do. We're going to look at it slowly, in the quiet, together. Before we begin walking, let me sit for a moment longer with what this system actually is, because it deserves it, and because knowing it makes the rest of the night land harder. Alpha Centauri is not just a name on a chart. To the people of the southern half of our world, the 2 brighter stars of the system are visible together as one of the brightest points in the whole night sky. A single brilliant star that has guided travellers and been woven into stories for as long as there have been people to look up. What the eye sees as one light is really that pair of suns, so close together at this distance that they blur into a single point, and hiding near them, far too faint to see, is the little red one, Proxima, the actual nearest of the 3, discovered only a little over 100 years ago because it is so dim it escaped notice for all of history before that. So this is not some abstract faraway thing. It is a light people have looked at with their own eyes across all of time, a bright familiar star in the southern sky, and it turns out to be the closest doorway out of everything we know. That is part of what makes it such a fitting place to begin. It is close enough to see, close enough to name, close enough to have a real planet we have measured. Everything about it says, this one surely we could reach, and that is exactly the promise the rest of tonight is going to slowly, gently take apart. Let me start with the part everyone thinks they understand, the distance. Because before we get to the strange barriers, the ones that hide inside time and inside our own decisions, we have to sit with the plain physical gap, and we have to be honest about how large it really is. And the honest version is the first place the journey starts to feel less like a trip and more like something else. Every number that tells you how long it takes to reach the nearest star is built the same simple way. You take the distance, which does not change, and you divide it by the speed you can travel, which we cannot make large. That is the whole calculation. And because the distance is fixed at 40 trillion kilometers, the entire story of how long the journey takes is really a story about how slow we are. Let me give you the honest anchor first, the one that sets the scale. The fastest object human beings have ever launched away from the Sun is a small, old spacecraft called Voyager 1. It left Earth in the autumn of 1977, before most people watching this were born, and it has been falling outward ever since, faster than anything we have ever sent in that direction. It moves at about 17 kilometers every second. Let that sink in for a moment, because it is genuinely fast. 17 kilometers per second is around 61,000 kilometers per hour. At that speed, you would cross the entire United States in about 4 minutes. It is far beyond any rocket, any jet, any bullet. It is, as far as leaving the Sun behind goes, the human record. Sometime around the middle of November in the year 2026, Voyager 1 passes a quiet milestone. It becomes the first thing humans ever made to be a full light day away from home, which means the light it faintly sends back now takes an entire day to reach us. That is a beautiful and lonely fact. And here is the thing that turns it cold. If you took that record-breaking spacecraft, the fastest object our species has ever flung outward, and you pointed it straight at Proxima Centauri, and you let it run, it would take somewhere around 73,000 years to get there. 73,000 years. Not 73, not 700, 73,000. I want you to feel how long that is in human terms, because the number is so large it goes numb if you do not slow down with it. 73,000 years ago, there were no cities, no farms, no written words, no wheels. Our own species had barely begun to spread out across the Earth. If a group of those early humans had somehow launched a Voyager toward the nearest star at the dawn of everything we have ever done, all of recorded history, every empire and every song and every person you have ever heard of, all of it would have happened while that ship was still in the early part of its trip, and it would still not have arrived. The entire span of human civilization, from the first cave painting to this moment, would be a small opening act, and the ship would still be out there in the dark, most of the way still ahead of it. That is what the nearest star costs at the fastest speed we have ever actually achieved, and I want to be fair to Voyager here, because it is easy to say it is slow, and it is not slow. It is the fastest thing we have ever made move away from the Sun, and it got that speed not just from its rockets, but from clever gravitational slingshots past the giant planets, borrowing a little of their motion to fling itself onward. There is no more speed to be had that way. It is coasting now, and it will coast forever, and 17 kilometers per second is simply what falling away from the Sun looks like when you do it as well as we currently know how. To go meaningfully faster, you do not just need a bigger rocket. You need a fundamentally different kind of engine, one we have sketched on paper but never built and flown. There is a reason for that, and it is worth understanding because it is the quiet root of the whole speed problem. A rocket moves by throwing mass out the back. To go faster, you throw more, which means you must carry more fuel, which makes the rocket heavier, which means you need still more fuel to move that fuel. The demand does not grow gently. It grows in a way that spirals out of control, so that reaching even a small fraction of light speed with a chemical rocket would require more fuel than exists in the solar system. Far more, absurdly more. The rocket that could reach the nearest star quickly, built the ordinary way, would need to be larger than a planet, almost all of it fuel to deliver a single small capsule to Proxima. That is why the fast starship is not a matter of trying harder with the tools we have. The tools we have cannot do it at all. Every serious plan has to abandon the ordinary rocket entirely and reach for something exotic, and even the exotic plans, as we are about to see, buy you only so much. Now, of course, engineers know Voyager is slow by the standards of what we can imagine, so they have spent decades asking a better question. What if we went faster? What if we built something designed, from the beginning, to cross that gap? And when you climb that ladder of imagined speed, the numbers do come down, but watch how they come down, because the pattern tells you something. If you could build a ship that travels at 1% of the speed of light, which is already almost unthinkably fast, around 3,000 kilometers every second, the crossing to Proxima would take about 424 years. Better than 73,000, yes. But 4 centuries is still longer than most nations have existed. A ship launched when the first telescopes were being pointed at the sky would only now be arriving. Push harder. In the 1960s, the physicist Freeman Dyson sketched a design that might reach around 3% of light speed by riding on the pulses of nuclear explosions. At that speed, the trip is about 129 years. In the 1980s, a study called Project Longshot imagined something near 4.5% of light speed, which brings the journey down to roughly 94 years. Closer to a single long human lifetime, but only barely, and only for a machine, not a person who has to live every one of those years awake inside a box. Then you reach the boldest serious designs. In the 1970s, the British Interplanetary Society worked out a concept called Project Daedalus, a fusion-powered probe the size of a skyscraper, weighing something like 54,000 tons, most of it fuel. Daedalus was meant to reach about 12% of the speed of light. At that blistering pace, the crossing to the nearest star drops to about 35 years. And in 2016, a project called Breakthrough Starshot went further still, imagining tiny sails, each no heavier than a gram, pushed by an enormous ground-based laser, up to around 20% of the speed of light. At 1/5 of light speed, the trip takes only about 21 years, plus, of course, another 4 years and change for any picture it takes to crawl back home to us at the speed of light. 21 years. That is the very best case, the most optimistic number in the entire field, and it belongs to a mission that carries nothing but a camera the size of a postage stamp. And notice what we had to do to get there. We had to imagine lasers we cannot build, sails we cannot yet make, and energies that dwarf anything humanity currently produces. And even then, even in that dream, the nearest star is decades away. I want to be honest with you about the difference between these numbers and reality, because it matters. Every one of the faster figures I just gave you comes from a design that has never been built and never flown. Project Daedalus was a study, a careful and serious one, but it existed only on paper, and it called for fuel that we would have to mine from the atmosphere of a giant planet, and an engine-burning fusion in a way we still cannot sustain in a laboratory for more than moments. Breakthrough Starshot is a research program, not a spacecraft, and the laser array it would need does not exist and might cost more than the wealth of nations to build. So when you hear 21 years, or 35 years, remember that these are the travel times of ships that live only in equations. The real crossing time, using the fastest thing we have actually launched, is still that first terrible number, 73,000 years. Let me set that against something you can picture. The oldest structures our species has built, the great stone monuments and the first cities, are only a handful of 1,000 years old. Everything written down, every name we still remember, fits inside the last 5,000 or 6,000 years. If, at the very dawn of all of that, at the building of the first stone walls, someone had launched our fastest real spacecraft toward the nearest star, it would today have covered only a small fraction of the trip. It would not be 1/10 of the way there. All of history, from the first written word to this moment, is a fraction of a single crossing, at the only speed we can truly reach. That is the gap between what we can build and what we would need. The dream ships close that gap on paper. In the real world, the nearest star is still tens of thousands of years away, and the closing of that gap is a hope, not a plan. And underneath all of it sits the wall that never moves. Light itself, the fastest thing that can exist, the absolute speed limit of the universe, takes 4.24 years to make the trip, and light never slows down, never gets tired, never has to carry fuel. 4 years and change is the floor. Nothing can beat it. And everything we could ever actually build is far, far slower than light. So the best we can honestly hope for is a journey measured in decades, and the realistic versions are measured in centuries or in tens of thousands of years. This is the first barrier, and I want to name it clearly before we move on, because we are going to keep adding to it. Call it the speed you cannot beat. The nearest star is so far, and we are so slow, that the crossing is longer than a human life in every plan that has any chance of working, and longer than human history in the plans we can actually build today. Most people, when they think about why we have not gone to the stars, stop right here. They think the whole problem is distance and speed, but distance is only the first wall. It is the one everyone talks about, and it is, believe it or not, the easiest of the 4 we are going to meet tonight. Because at least distance is honest. At least distance stays where it is. The next barrier is not so kind, and it begins the moment your fast ship is actually moving through what we wrongly call empty space. We have a habit of calling the space between the stars empty, and in a way it is. If you scooped up a handful of it, you would find almost nothing at all. But almost nothing is not the same as nothing, and the difference between those two things becomes deadly the moment you start moving fast. This is the second barrier, and it is a strange one because it turns the very emptiness we admire into a weapon aimed at anyone trying to cross it. Let me describe what is actually out there. The sun right now sits inside a thin wisp of gas called the local interstellar cloud, and that cloud holds about 3/10 of an atom in every cubic centimetre of space. Around it lies an even emptier region called the local bubble, thinner still, sometimes only 1,000th of an atom per cubic centimetre. These are numbers so small they barely mean anything. A single breath of the air in your room contains more atoms than a stretch of interstellar space the size of a house. By every ordinary standard, it is a vacuum, cleaner and emptier than anything we can make in a laboratory on Earth. If you were floating out there, drifting slowly, it would do nothing to you at all. You could pass through it for 1,000 years and never notice a thing. But you're not drifting. You're trying to reach the nearest star, which means you're trying to go fast, and speed changes everything about that thin scattering of atoms. Here is the piece that surprises people. When you fly through gas at a tiny fraction of light speed, those individual atoms are no longer gentle. From the ship's point of view, it is not moving through still gas at all. It is standing still while a torrent of atoms slams into it at 1/10 the speed of light. And a single hydrogen atom, the lightest, simplest thing there is, striking you at that speed, carries an energy of nearly 5 million electron volts. That is the kind of energy we normally associate with nuclear radiation. Not one atom, once. A continuous, endless sleet of them, pouring against the front of the ship every second for the entire length of the journey. The emptiest thing in the universe becomes a steady rain of radiation, simply because you dared to move through it quickly. It helps to remember why this happens, because it is one of those truths that feels wrong until you look at it directly. Energy of motion does not depend only on how heavy a thing is. It depends far more on how fast it is going, and it climbs with the square of the speed. Double the speed, and you quadruple the punch. This is why a mosquito drifting into you is nothing, and why the same mosquito would be a bullet if it were moving fast enough. Out in interstellar space, the atoms are not moving fast, but you are, and from your point of view that makes no difference at all. What matters is the speed between you and them. So a single hydrogen atom, the smallest possible speck of ordinary matter, the lightest thing that exists, becomes a tiny needle of nuclear energy the instant your ship is moving fast enough to matter, and there is no way to sweep the path clear ahead of you. The atoms are everywhere, evenly scattered, and you must plough through all of them, one after another, for 4 light years. Engineers who take this seriously talk about needing a kind of shield out ahead of the ship, sometimes a physical plate, sometimes a cloud of material deliberately spread in front to absorb the worst of it before the crew compartment arrives. They have even imagined a droplet of gas or a thin disk of matter flown ahead like a windshield, sacrificing itself so the ship behind survives. But every one of these ideas runs into the same wall we've already met. Anything you carry to protect yourself, you first had to accelerate to the same enormous speed, and that costs energy you do not have and adds mass that slows you down. The protection and the propulsion fight each other. The faster you go to shorten the trip, the more the emptiness tries to kill you, and the more shielding you need, and the heavier and slower you become. You cannot win the argument. You can only choose which way to lose it, and atoms are the small problem. Scattered through that same thin space are grains of dust. Not many, and not large. A typical one might weigh a fraction of a millionth of a gram, a speck far too small to see. Out there, floating, it is harmless. But strike it at 1/10 the speed of light, and the arithmetic becomes something out of a nightmare. A grain weighing just 1 gram, about the weight of a paperclip, hitting your ship at that speed, releases energy equal to more than 100 tons of dynamite. Even a speck 100 times lighter than a grain of sand delivers the punch of 11 kilograms of high explosive. At the speeds we would need to reach the nearest star in any reasonable time, the ship is not gliding through a peaceful void. It is being shot at, without pause, by the vacuum itself, with bullets made of single specks of dust, each one arriving with the force of a bomb. There is no easy shield against this. You might imagine armouring the front of the ship, and engineers have thought hard about exactly that, about whether a thick plate or a cloud of protective material out ahead could take the hits. but every kilogram of shielding is a kilogram you first had to accelerate to that same terrible speed, which costs more fuel, which makes the ship heavier, which makes it harder to move at all. And there is a cruel twist buried in the physics. When high-energy particles smash into thick shielding, they do not simply stop. They shatter, and the fragments spray outward as a shower of secondary particles, sometimes doing more damage on the inside than the original strike would have done on the outside. In certain cases, adding shielding makes the radiation worse, not better. And then, quietly in the background, there is the ordinary radiation of open space, the kind our own astronauts already worry about on much shorter trips. We have measured it. When one of our robotic missions crossed from Earth toward Mars, its instruments recorded a radiation dose of about 1.8 thousandths of a sievert every single day, adding up to roughly 2/3 of a sievert per year, just from the natural sleet of cosmic rays that fills the space between worlds. On a trip to Mars, lasting months, that is already a serious health problem for a human crew. Now stretch that trip out to decades, or to centuries, the honest length of a journey to the nearest star, and the numbers climb into ranges the human body simply cannot survive. There is not enough shielding you can realistically carry to hold it back for that long, and it is not only bodies that this radiation attacks, it attacks machines too, quietly, relentlessly. Every high-energy particle that strikes a computer chip can flip a bit, corrupt a memory, damage a circuit. On our satellites, close to home and protected by the Earth's own magnetic shield, engineers already have to design around this, building in ways to catch and correct these errors before they cause harm. Now imagine a ship that must run flawlessly for decades or centuries in the full blast of interstellar radiation with no planet's magnetic field to hide behind, its computers and its life support and its engines soaking in a storm that shreds electronics as surely as it shreds cells. The machinery that keeps the crew alive is being degraded by the very same crossing it is trying to survive. Over the length of a real interstellar journey, the ship does not simply need to be built well. It needs to keep repairing itself faster than the emptiness takes it apart, for longer than any machine we have ever made has run. Think of how few of our creations still work after even 50 years, and then ask one to run flawlessly, unattended in a radiation storm for 2 or 3 or 10 times that long, with no one able to send it a spare part across 4 light-years of dark. The ship must not only survive the crossing, it must repair, rebuild and renew itself the entire way, a small closed world keeping itself alive by its own hands, for a span of time that dwarfs the working life of anything we have ever built. There is a clever old idea for dealing with the impacts, worth mentioning because engineers still reach for it. Instead of one thick wall, you use several thin ones, spaced apart, so that a dust grain shatters against the first layer and spreads its energy into a spray that the later layers can absorb. It is a trick already used to protect spacecraft near Earth from small debris, and it works, up to a point, for slow impacts. But at a fraction of light speed the energies are so enormous that even this only softens the blow rather than stopping it, and every extra layer is more mass to accelerate and carry. So the same trap closes again. Every gram of cleverness you add to survive the crossing is a gram you must first fling across 4 light-years, which costs energy you do not have and slows the ship you are trying to speed up. The emptiness does not need to be dense to defeat you. It only needs to be there, and to be crossed fast for a very long time. So step back and see what the second barrier really is. The distance was bad enough, but now we learn that the crossing itself is not a calm coast through nothing. It is a slow erosion. Every day of that decades-long or centuries-long journey, the ship and everyone in it is being sandblasted by atoms, bombarded by dust with the force of explosives, and soaked in a radiation bath that no practical wall can fully stop. The traveller does not simply have to endure the length of the trip. The trip actively works to take the traveller apart, a little at a time, the whole way. The emptiness between the stars, the thing that looks so peaceful and still when you gaze up at it, is exactly full enough to wear down the ship, the body, and the plan, one atom at a time, across a distance already too long to finish. There is an image that captures this well, and it comes from something you have felt yourself. Think about driving through a light rain at night. Standing still, the rain is gentle, a soft mist you could walk through without a thought. But get in a car and drive fast, and suddenly that same gentle rain becomes a hard, streaking rush against the windshield, drops turning to lines, the whole world ahead resolving into a blur of oncoming water. Nothing about the rain changed, only your speed. Now imagine that instead of water, the drops are atoms and grains of stone, and instead of a highway you are moving at 1/10 the speed of light, and instead of minutes the drive lasts for decades or centuries. The front of an interstellar ship is a windshield in an endless storm, and the storm never eases, and there are no wipers, and every drop carries the energy of radiation or the punch of an explosion. The gentle emptiness becomes a gale the instant you try to cross it quickly, and it blows against you the entire way. And unlike a rainstorm, this one leaves marks that add up. Every atom that strikes the front of the ship deposits a little energy, heats it a little, damages it a little. Over years, the leading face of the ship would be slowly eroded, pitted, worn thin, sandblasted by the very emptiness it is trying to cross. Engineers have to imagine the front of a starship not as a smooth nose cone, but as a shield that is being steadily consumed, a sacrificial face that must be thick enough to last the whole journey without wearing through, and every bit of thickness is more mass, and more mass is more fuel, and more fuel is a slower ship, and the whole miserable knot pulls tighter. The faster you go to beat the distance, the harder the emptiness scours you, and the more armour you need, and the harder it becomes to go fast at all. The storm and the speed are the same thing, and you cannot have one without the other, and we still have not reached the strangest barrier. Because so far, everything we have talked about is at least the kind of problem an engineer could dream of solving, with enough time and enough cleverness. Go faster, build a better shield. These are hard problems, maybe impossible ones, but they are the familiar shape of hard. The next wall is different. The next wall is the one that turns a successful, fast, well-shielded journey into a failure anyway, and it does it with nothing more than the plain fact that what goes fast must somehow slow down. Here is a question that sounds almost too simple to matter, and it is the question that quietly destroys most of our dreams of reaching the stars. When your ship finally gets to the nearest star after all those years, how does it stop? We do not usually think to ask this. When we imagine going somewhere, we picture the arriving, the standing still at the end, the stepping out. Stopping feels like the easy part, the part that just happens when you get there. But in space, stopping is not free, and it is not automatic. In space, slowing down is its own enormous task, every bit as hard as speeding up, and often harder. This is the third barrier, and it is the one that turns reaching the nearest star into passing the nearest star, which is not the same thing at all. Think about what it took to get up to speed in the first place. To reach 20% of the speed of light, you had to pour in a truly enormous amount of energy, whether from fuel you carried or from a giant laser pushing you from behind. Now, you're cruising toward Proxima at 1/5 the speed of light, and the star is coming up ahead. To actually arrive, to enter that system and stay, you have to shed all of that speed again. You have to do the entire acceleration in reverse, and here is the trap. If you planned to slow down by burning fuel, then you needed to carry all that slowing down fuel with you the whole way, which means you had to accelerate it too, at the start, along with everything else. The fuel you need to stop makes the ship heavier, which means you need more fuel to get it moving, which means it is heavier still. The problem feeds on itself, and the numbers explode until the ship becomes impossibly, ridiculously large. Carrying your own brakes across 4 light years is, for the fast missions, simply not possible. So what do the boldest designs actually do about this? Mostly, they give up on stopping. Look closely at Breakthrough Starshot, that beautiful idea of tiny laser-push sails reaching the nearest star in about 21 years. Read the fine print, and you find something quietly devastating. Those sails have no way to slow down. None. They get shoved up to 1/5 of light speed by the laser here at home, and then they coast, and when they finally reach Alpha Centauri, they do not stop. They do not orbit. They do not linger. They tear straight through the entire star system in a matter of hours. Picture that. 21 years of travel, 40 trillion kilometers of dark, and then the whole destination, 2 suns and a red ember and a small locked world, rushes up out of the black, fills the view, and is gone, all in an afternoon. The little sail grabs whatever images it can as it flashes past, a few frames, a handful of seconds of data, and then the star shrinks behind it, and it sails on into the emptiness on the far side, falling forever toward nothing. I want to sit in that moment with you, because it is the heart of this barrier. Imagine you are aboard that probe. For 21 years there has been nothing but the dark and the faint red point growing slowly larger, and then, near the end, it stops being a point. It swells. The two brighter suns separate out, and the dim red one resolves, and there, crossing in front of it, a small round world. The planet we have wondered about for a lifetime. It fills the sky ahead. Your instruments are drinking in everything they can. Faster and faster, the light of another sun washing across your senses for the first time in the history of your kind. And there is no slowing. You cannot stop. The world crosses your view like a stone thrown past a window, here and then gone, and the suns slide backward, and the light dims behind you, and you are falling out the far side of the only destination you will ever reach, back into a dark that has no other shore. You did everything right. You crossed 4 light years, you aimed perfectly, and you did not, and could not, stay. Why is stopping so much harder than we expect? On Earth, stopping is easy, and it fools us. When you stop a car, the brakes do not have to store the energy of the whole trip. They rub against the road and the air, and all that motion bleeds away into heat, pushed off into a world that is happy to take it. When you stop by parachute, the air does the work. Every kind of stopping we know from ordinary life leans on something outside us. The ground, the air, the water, some great surrounding thing to push against. But in the space between the stars there is nothing to push against. There is no road, no air, no water. There is only the ship and the void. And so, to slow down, the ship has to do all the work itself, from its own resources, throwing mass out the front the way it threw mass out the back to get going. It has to unspend all the energy it spent, and it has to carry the means to do it the entire way. There is one clever idea that tries to slip past this, and it is worth naming because it is beautiful even though it barely helps. Instead of carrying fuel to brake, a ship might unfurl an enormous sail and use the destination star's own outpouring of light and particles to push back against it, slowing down against the wind of the star it's approaching. It is a lovely thought, arriving on the breath of the very star you're trying to reach. But it only works within a narrow window of speed and distance, and it requires the sail to be immense and nearly weightless, and to survive the crossing intact, and it still cannot bring a fast, heavy, crude ship to rest in time. For the tiny sail probes, it might one day work in some limited way. For anything carrying a living person, the brakes remain the problem that turns the whole beautiful plan into a flyby. And a flyby, when you have crossed 4 light years and given up everything to get there, is not arrival. It is the universe letting you look, once, at speed, and then carrying you on past forever. That is the difference between reaching a place and arriving at it, and the fast missions can only ever do the first. They can reach the nearest star, they cannot arrive there, and for a machine carrying a camera, maybe that is enough. A few photographs of another world, even seen in a single flash as you tear past, would be one of the greatest achievements in human history. But the moment you want to do more, the moment you want to orbit, to study, to land, to stay, and above all the moment you want to carry people, the flyby is not arrival, and the deceleration problem becomes a wall you cannot go around. The engineers know this, and some of them have tried to design the brakes back in. The original Project Daedalus was, like Starshot, a flyby, a probe that would rip through the target system and gather what it could on the way past. Years later, a follow-up study called Project Icarus set out specifically to solve the stopping problem, to add a way to slow down at the end. And what they found was that braking is brutally expensive. To shed that speed, you either carry a second engine and a second ocean of fuel, doubling down on the impossible rocket, or you unfurl an enormous sail and try to brake against the destination star's own wind and light, which only works within a narrow band of speeds and distances and requires the target star to cooperate. Every path to stopping adds mass, adds complexity, adds points of failure, and pushes the mission further out of reach. There is a symmetry here that is almost cruel in its neatness. To reach the star, you must build up speed, and building up speed is enormously hard. To arrive at the star, you must shed that same speed, and shedding it is at least as hard again. So arrival, real arrival, costs you the whole difficulty twice, once to go and once to stop, and the second half is the half that everyone forgets, and that quietly ruins the plan. It is as though the universe charges you a fare for the journey, and then, just as you reach the door, charges you the entire fare a second time to be allowed to step off. A ship budgeted only for the going gets to the star and cannot pay the second fare, and so it does not step off. It sails on by. This is why the honest interstellar mission designers draw a sharp line between two very different things that ordinary language blurs together. There is the flyby, where you build up speed, cross the gulf, and rush through the target system gathering what you can as you pass, never stopping, carried on into the further dark. And there is the rendezvous, where you not only cross the gulf but also arrive, matching speed with the destination, entering orbit, staying. The flyby is merely very, very hard. The rendezvous is harder by a wide margin, and for a ship carrying living people, it is the only kind that counts, because you cannot ask a crew to spend their whole lives crossing to another star only to blow through it in an afternoon and die coasting away on the far side. For them, arrival is the entire point, and arrival is precisely the part the physics makes hardest of all. So notice where we are now. We have 3 barriers stacked on top of one another. The distance is longer than a lifetime. The crossing erodes the ship the whole way. And now, even if you survive both of those, the fast ship cannot stop, so the ship that reaches the nearest star does not arrive at the nearest star. It merely passes through and falls onward into the further dark. The physics has quietly rewritten our sentence. We wanted to say, we reached another star. What the universe lets us say instead is, we passed another star, at a speed that made stopping impossible. That is a different sentence, and the word arrive has gone missing from it. Let me pause here, because we have covered a lot of ground, and it would be easy to feel the barriers piling up faster than you can hold them. So before we go further, before we meet the strangest wall of all, let us stop for a moment, gather up what we have found, and set the pieces side by side in the quiet. Because when you line them up, a pattern starts to show through, and the pattern is the real story of tonight. Let us take a slow breath and stand still for a moment in the middle of this journey, because we have gathered 3 heavy things and it is worth holding them all at once before we pick up the 4th. When we began, the problem seemed simple, almost obvious. The nearest star is far. That was the whole difficulty, we thought. Distance. And we found that the distance is indeed worse than most people imagine. At the fastest speed we have ever actually achieved, the crossing takes 73,000 years, longer than all of human history. At the fastest speed we can seriously dream of, it still takes decades, and only for a tiny machine, not a living person. That was the first wall, and if it were the only one, we could at least tell ourselves a hopeful story. We could say, give us enough time, enough cleverness, enough patience, and one day we will build something fast enough, and we will make the crossing. Distance is a wall you can imagine climbing, slowly, over centuries. But then the second wall appeared, and it was subtler. The empty space we have to cross is not truly empty, and at high speed its thin scattering of atoms and dust turns into a continuous storm of radiation and tiny explosions that wears the ship down across the entire trip. The very speed that shortens the journey is the same speed that turns the emptiness into a weapon, and there is no shielding light enough to carry and strong enough to hold it all back for decades or centuries. So the crossing does not just take a long time, it actively erodes whatever tries to make it. And then came the third wall, the one almost nobody thinks to check. Even if you go fast, and even if you survive the crossing, you still have to stop, and stopping is as hard as starting, often harder. The fast ships have no brakes. They reach the star and tear straight through it in an afternoon, and fall out the other side into the dark. They can reach the nearest star. They cannot arrive there. The physics keeps quietly swapping the word we want, arrive, for a word we did not choose, pass. Now here is what I want you to notice, lying there in the quiet, because this is the turn the whole night has been building toward. Look at those 3 walls again. The first one, distance, is about how far the star is, but the second and the third are not really about distance at all. The erosion of the crossing and the impossibility of stopping would be problems even if the star were closer. They are problems about speed, about matter, about energy, about the plain physics of moving a heavy thing across a great gap and bringing it to rest at the far end. Distance is only the first of the reasons you never arrive, and it turns out to be the shallowest one. The harder reasons have nothing to do with how many light years lie between us and Proxima. They have to do with the nature of the crossing itself. Let me put it another way, because I want this to settle in gently rather than all at once. Suppose a genie appeared and cut the distance in half. Proxima is now only 2 light years away instead of 4. Have we solved the problem? A little. The crossing times drop by half. but the erosion of the crossing is still there, just for a shorter stretch. The impossibility of stopping is exactly as bad as before, because stopping does not care how far you came, only how fast you're going when you arrive, and the barrier we are about to meet, the one made of decisions, does not shrink at all, so halving the distance helps only the one wall that was already the least of our worries, and leaves the others standing. That is how you know the distance is not really the heart of it. You can imagine the star much closer, and most of the difficulty survives untouched. This is the strange gift of laying the pieces out in the quiet like this. It shows you that the thing you thought was the whole problem is only the surface of it, and it prepares you for the turn we are about to take, which goes somewhere you would never expect a problem about the stars to go. It goes inward, away from the physics of engines and dust, and into the plain arithmetic of when a sensible person should choose to leave. That is the pattern. That is the thing the whole journey reveals when you lay the pieces side by side. We started out thinking the nearest star was hard to reach because it was far away, and we are discovering, wall by wall, that the distance is almost a distraction. The real barriers are stranger and closer to home than that, and the strangest one of all, the fourth wall, the one we are about to meet, is the closest to home of any of them, because it does not live in space at all. It does not live in the atoms or the dust or the physics of stopping. It lives inside the mind of anyone who tries to decide when to leave. Hold on to that, and let us walk into it gently, because it is the most beautiful and the most unsettling part of the whole story. Imagine you are standing beside a finished starship. It is done. Every problem we have talked about so far, you have somehow solved. You have a ship that can reach a good fraction of light speed. You have shielding enough to survive the crossing. You have brakes, real ones, so this ship can actually stop at the far end and stay. It is fueled. It is crewed. It is ready to go. The only thing left is to decide to launch, and I am going to show you why. If you are thinking clearly, you do not. This is the fourth barrier, and it is not made of physics. It is made of reasoning, of nothing more than a sensible person doing the math and making the rational choice. It has a name. In the year 2006, an engineer named Andrew Kennedy published a paper with a quiet title about what he called the weight calculation and the incentive trap of progress. And the idea inside it is one of those simple thoughts that, once you see it, you cannot unsee. Here is the thought. Our ability to travel fast has been growing over time, slowly, unevenly, but growing. Each generation can build ships that go a little faster than the last. Kennedy models this as a long-run growth in achievable speed of very roughly 1.5% per year. Now suppose you launch your finished starship today, at today's best speed, toward the nearest star. It sets off into the dark on a journey of many decades. But back home, progress does not stop the day you leave. Engineers keep working, speeds keep climbing, and a few decades after you depart, someone builds a ship that is meaningfully faster than yours. They launch it, and because it is faster, it catches up to you out in the dark, passes you, and reaches the star first. You spent your whole journey being overtaken by a ship that left long after you did. You arrive second to find your own descendants already there, having passed you somewhere in the emptiness while you slept. Sit with how strange that is. You did not fail because the star was too far or the crossing too harsh. You failed because you left too early. And now ask the obvious next question, the one that springs the trap. If leaving today means being overtaken, then when should you leave? And the answer the math gives back is chilling in its reasonableness. For many nearby destinations, the calculation says you should wait, not a little, sometimes centuries. You should sit at home, not launch, and let the technology keep improving, because a ship that leaves much later and travels much faster will arrive sooner than one that leaves now. The rational move, the smart move, the move that actually gets a traveller to the star soonest, is to not go yet. And here is where the trap closes, quietly, without a sound. Because that reasoning never expires. Tomorrow the same logic applies again. Progress is still continuing, so a ship launched even later will be faster still, so once again the smart thing is to wait a little longer. The line marked leave now keeps sliding forward into the future, staying always just ahead of you, exactly as fast as our cleverness advances. Every generation, standing beside its own finished starship, runs the same honest calculation and reaches the same honest answer. Not yet. Wait for the better ship. And so the launch that makes sense to begin is always the one you begin later, and later never comes, because later is always still improving. I want you to stand in that moment on the launch pad and feel it. The ship is ready. The crew is ready. And the mathematics, cold and correct, says do not go. A faster ship built 40 years from now will pass this one in the dark. So the engines stay cold. The crew stands down. The decision, sensible and right and unbearable, is made to wait for the better ship. And then it is made again, in the next generation, and the next, each time for exactly the same good reason. Nobody is wrong, nobody is foolish. Every single person who chooses to wait is choosing correctly, and that is the horror of it. This is a barrier built entirely out of good judgment, a wall assembled from reasonable choices, each one sound, that together keep us home forever. You already know this trap, by the way, in a much smaller and more familiar form. You have felt it whenever you tried to decide when to buy a computer, or a phone, or any piece of technology that keeps getting better and cheaper. If you buy today, next year's model will be faster and less expensive, and you will feel a little foolish, so you wait. And next year, the same is true again. And if you followed that logic without limit, you would wait forever and never buy anything at all because there is always a better version coming. Kennedy's insight was that the journey to the stars is exactly this dilemma, blown up to the scale of centuries and civilizations. The starship is the ultimate expensive gadget that keeps improving, and the rational buyer keeps waiting for the better model, and the better model keeps coming, and so no one ever buys, and no one ever leaves. He worked through the numbers for real destinations. For a nearby star like Barnard's star, feeding in a modest long-run growth in our speed, the math says the best time to depart is not now, but centuries from now, because a ship that waits for that maturity and then goes fast will pass any ship foolish enough to crawl off early. The optimal move is patience, on a scale longer than nations last, and the cruelty is that patience is not a settled state. It is a decision you have to keep making, and every time you make it, the same reasoning applies, so the departure date keeps sliding away from you, always a little further out, always for a perfectly good reason. The barrier is not that we lack the will to go. It is that going is, quite genuinely, the wrong move, again and again, forever. We are not failing to leave. We are correctly declining to, every single time. And there is one more turn of the screw. Even the people who did leave, in the moment they left, could not know they had chosen the right time. They could only hope. Somewhere behind them in the dark, a faster ship might already be gaining. Every traveller who ever departs carries that quiet uncertainty with them the whole way. The knowledge that they might be the ones who left, not the ones who arrive, overtaken in the emptiness by children not yet born on the day they said goodbye. There is a loneliness in that which has nothing to do with distance, and everything to do with time, and it is a loneliness the physics guarantees. Now widen the view from the single traveller to the whole society that would have to send them, because the trap bites there too, and in a way that is harder to escape. Imagine a civilization deciding whether to pour its wealth into a starship now, or to wait and invest in the research that will make a better starship later. The weight calculation whispers the same answer to the society that it whispers to the traveller. Do not launch yet. Spend on progress instead, because progress will get someone there sooner, and so the resources that might have built a ship are, quite reasonably, spent on making a future ship better, generation after generation, and the launch keeps not happening, not out of cowardice or poverty, but out of a sound investment strategy that never reaches its own conclusion. A civilization can spend 1,000 years getting ready to go to the stars, doing everything right, and never go, because at every step the smart move was to prepare a little more. And here is the part that turns it from a curiosity into something close to tragic. It is entirely possible that this is not a temporary phase but a permanent condition. As long as our capabilities keep improving, even slowly, the weight remains rational, and the departure keeps receding. The only way the trap ever springs open is if progress finally, truly stops. If our speed stops improving so that waiting no longer buys you a faster ship. In other words, the only time it becomes rational to actually leave for the stars is when we have stopped getting better at leaving. A civilization at the height of its cleverness is exactly the one most tempted to wait. A civilization that has stopped advancing is the one for which going finally makes sense. And that is a strange and sobering thought, that the door to the stars may open only for those who have stopped growing and stay closed for everyone still climbing. So this fourth wall is not really a wall of steel or distance at all. It is a wall of reasons, and it is the strangest kind of barrier there is, because you cannot break through it by being smarter or braver or more determined. Being smarter makes it worse. Being determined does not help, because the determined thing to do, the correct thing, is still to wait. It is a barrier that grows stronger the harder you push against it with cleverness, and only weakens if you stop. And this is why, of all 4 walls, it may be the one that keeps us home the longest. Notice how different this wall is from the others. The distance is out there in space. The erosion is out there in the dust. The stopping problem is out there in the physics of engines and fuel. But this one, the weight calculation, is not out there at all. It is in here, in the mind, in the very act of deciding. It is the first barrier that has nothing to do with the star and everything to do with us. The universe is not stopping us now. We are. Correctly. And there is a particular kind of grief in that. The grief of being held back not by an enemy, not by a wall of stone, but by your own clear thinking, which never makes a mistake and never lets you leave. There is a version of this that stings even more, and it is worth naming before we move on. Even if a civilization somehow broke the trap, even if it collectively decided to launch, and to keep launching, the ones who left first would spend their entire journeys knowing they might be overtaken, knowing that the wave of faster ships behind them could sweep past at any time. Every traveller carries the quiet knowledge that they may not be the ones who arrive, only the ones who left. And so the nearest star recedes behind a horizon made not of space, but of the promise of a faster tomorrow, a promise the universe keeps just often enough to keep everyone standing on the pad, looking up, not leaving. This is the 4th wall, the strangest of them all, and with it the shape of the whole problem finally comes clear. But there is still one more comfort to take away, one loophole people always reach for when the distances get too large, and we have to close it too. It is the hope that speed itself might bend time in our favour. It does, just not nearly enough. Whenever the distances to the stars get too large to bear, people reach for the same beautiful escape hatch, and it is worth reaching for because it is real. The escape hatch is time itself. One of the most extraordinary discoveries in all of physics is that time is not the same for everyone. The faster you move, the more slowly your own clock ticks compared to the world you left behind. This is not science fiction, and it is not a trick of the imagination. We have measured it, over and over, with clocks on aircraft and clocks on satellites. Move fast enough, and you could, in principle, cross a great gulf of space while only a little time passes for you. A traveller might step aboard a fast enough ship, cross to a distant star, and step off having aged only a few years while long ages passed at home. This is the loophole that could, in theory, make the stars reachable inside a single human life. So let us reach for it honestly, and see how far it actually gets us. And the answer, sadly, is not far, because this gift only opens up when you get truly close to the speed of light. At the speeds we could ever realistically build, the effect is almost nothing at all. Let me give you the number, because it is the number that closes the hatch. At 1/10 of the speed of light, which is already far beyond any ship we know how to make, the slowing of time is only about half of 1%. Half a percent. That means if the journey takes 100 years by the clocks back on Earth, the crew ages about 99.5 years instead of 100. They save 6 months over a century. That is the entire gift of time dilation at 1/10 of light speed. It does not compress the journey. It does not let anyone skip the decades. The crew lives through very nearly the whole crossing in real time, awake, aging, year by year by year, just like everyone they left behind. People sometimes imagine time dilation as a dial we could simply turn up, going a little faster to save a little more time in a smooth and generous trade. But the trade is not smooth at all. It is almost nothing until you get very close to light speed, and then it grows explosively in the last sliver before that limit. At half the speed of light, your clock runs slow by only about 13%. You have to reach around 90% of light speed before time slows to roughly half, and to get the dramatic effect, the one where long ages pass outside while mere years pass within, you must press right up against the speed of light itself, to 99.9% and beyond. And every step closer to that limit costs disproportionately more energy than the last, climbing toward infinity as you approach the wall that nothing with mass can cross. So the gift of time dilation is real, but it is hoarded behind the most expensive speeds there are, the very speeds our engines cannot touch. At the speeds we could plausibly reach, the dial has barely moved. There is a hard little irony in this. The one effect that could rescue a traveller from the length of the journey only becomes generous at exactly the speeds that make the journey most lethal, where every atom of the interstellar sleet strikes with the most force and every grain of dust becomes the most violent bomb. The universe offers the shortcut and the killing blow in the same package, at the same speed, so that reaching for the one guarantees the other. You cannot take the mercy without the wound. And at every speed gentle enough to survive, the mercy simply is not there. So the loophole is not merely shut, it is guarded, and the guard is the very danger of the speeds required to open it. To actually get the dramatic effect, the one where you cross the galaxy in a lifetime, you would need to be travelling at 99% of light speed, or 99.9 speed so far beyond our reach that talking about them is like a person who cannot yet swim planning to cross an ocean by holding their breath. At the speeds that are merely impossibly hard, rather than physically absurd, time dilation gives you almost nothing. So the traveller gets the worst of both worlds. The trip is long enough to swallow a career or a whole life, and the one physical effect that could have shortened it stays shut, because we cannot go fast enough to open it. There is a famous story physicists tell to explain time dilation, and it is worth telling here softly, because it shows both the promise and the heartbreak of it. Imagine two twins. One stays home on Earth, and the other boards a ship and travels very fast, out to a distant star and back. Because the travelling twin moves so quickly, their clock ran slow, and when they return they are younger than the twin who stayed. They might come back having aged only a few years, to find their brother or sister grown old or gone. It is a true consequence of the way the universe is built, and it has been confirmed in small ways with real clocks. It is the closest thing physics offers to a door through the wall of distance. But look closely at what that story quietly requires. For the travelling twin to come back barely aged, they had to move at very nearly the speed of light for the whole trip. That is the part we cannot do. At the speeds we can actually reach, the travelling twin comes home essentially the same age as the one who stayed, having gained nothing but the years of the journey. The magic only switches on at the very edge of light speed, in a regime our engines cannot touch and may never touch. So the twin story, which sounds like hope, is really the same closed door wearing a friendlier face. The shortcut exists in the mathematics. It simply sits behind a speed we cannot pay for. And even if we could, notice what the twin story costs. The traveller who comes back young comes back to a world that has moved on entirely. Everyone they knew has aged decades while they aged a few years. To use the shortcut is to leap forward in time, away from everyone, arriving into a future where the life you left has already finished without you. The door, even when it opens, does not lead home. It leads to a later, stranger world, with your old life closed behind you. So whether the door is shut, as it is for us, or open, as it might be for some far future civilization, the traveller still loses the world they left. The years spent leaving are real years, subtracted from a real life, and no arrangement of clocks ever gives them back. It is worth pausing on how strange and beautiful it is that time bends at all, because most people never quite believe it, and it is true. Motion genuinely slows the passage of time, and gravity does too, and we have measured both with clocks so precise that we can see the difference between a clock on the floor and a clock on a high shelf. The satellites that guide us around our cities have to correct for this every moment, or their directions would drift and fail within hours. So time dilation is not a theory waiting to be confirmed. It is a fact we depend on daily. The universe really does hand out time unevenly, and in principle that unevenness is a door through distance. The tragedy is only in the size of the effect at the speeds we can reach, and in the price of the ticket, which is measured in a fraction of light speed we cannot buy. And I want you to notice one last quiet thing about this door, because it changes how the whole journey feels. Even in the dream where we could travel near light speed and use time dilation fully, the traveller does not conquer the distance. They trade it. They trade the years of the journey for the loss of the world they left. To arrive young at the far star, they must let the whole world they knew grow old and pass while they were in transit. There is no version of crossing this gap where you keep both, where you reach the star and also keep the home and the people and the moment you left from. The universe always takes one in exchange for the other. Whether the door is shut, as it is for us, or open, as it might be for some far civilization, the price is the same. To go is to give up return. To arrive is to arrive alone, into a time that has left everyone you loved behind. and there is a final quiet cruelty folded into this. Whatever time does pass passes fully back home. When you leave for the nearest star, the world you leave does not pause and wait for you. It keeps going, at full speed, every day. Children grow up. The people who waved you off grow old. By the time your ship has crawled its way across those decades, the home you left has moved on completely, whether or not your own clock ran a hair slower along the way. You do not step through a shortcut and emerge into a slightly later version of the world you knew. You emerge, if you emerge at all, into a future that has left you behind, having lived the whole long journey in real time to get there. So the loophole shuts. The one door in the physics that might have let a living person truly cross this gap and arrive, young, into a new place, only opens at speeds we cannot reach, and stays sealed at every speed we can. The years spent leaving are real years, subtracted from a real life, and no clock trick gives them back. That is the fourth wall completed, and now all four are standing. But I have been holding something back, something even more quietly devastating than any of the four walls, and it is time to open that door because it changes what all of this was even for. We have been asking how hard it is to arrive. We have not yet asked what is waiting if you do. Let us imagine, for a moment, that you beat all of it. Suppose you break every wall we have built tonight. You find a way to go fast enough. You survive the sleet and the dust and the radiation of the crossing. You solve the impossible problem of stopping, and you escape the weight calculation, and you make the journey and you actually arrive, a living traveller, whole, at the nearest star. You have done the impossible. Now the door of the ship opens, and you look out at the world you crossed 40 trillion kilometres to reach. What is there? I have to tell you what is there, because it is the twist that turns this whole story from sad to something quieter and heavier. The nearest potentially habitable world, Proxima b, that planet we have dreamed about, the one sitting at just the right distance from its star for liquid water, is almost certainly not a refuge at all. It is a place that would kill you in ways the empty crossing never could. Remember what kind of star Proxima is. It is a red dwarf, small and cool and dim, and Proxima b orbits it very close in, because that is the only place warm enough for water around such a faint ember. The planet is huddled up against its star at a distance far smaller than the space between our Sun and even its nearest planet. And red dwarfs, for all their dimness, are not gentle stars. They are famous for something violent. They flare. In May of the year 2019, astronomers were watching Proxima when the star did something extraordinary. In the space of about 7 seconds, it brightened by a factor of about 14,000 in ultraviolet light. 14,000 times brighter in 7 seconds. Try to picture standing on a world where your sun, without warning, in less time than it takes to draw a slow breath, blazes up 14,000 times more fiercely and pours ultraviolet fire across the sky. And this is not a once-in-a-lifetime event. Red dwarfs like Proxima flare like this often, throwing out bursts of radiation that would strip away the upper layers of a planet's atmosphere and scorch the surface again and again over the ages. Measurements suggest Proxima b is bathed in something like 400 times the X-ray radiation that Earth receives from our Sun. 400 times. Think about what those flares do to a world over time, because this is the slow tragedy hidden behind the sudden violence. A planet's atmosphere is not a permanent thing. It is held down by gravity, but it is constantly nibbled at from above by the wind and radiation of its star. A calm star like our Sun nibbles gently, and a world like Earth can hold its air for billions of years. But a red dwarf that flares 14,000 times brighter in 7 seconds, over and over, across the ages, does not nibble. It tears. Each great flare strips away a little more of the upper atmosphere, blasting it off into space, and a planet sitting as close to Proxima as Proxima b does has almost certainly had this done to it countless times. The most likely result after billions of years of that treatment is a world scoured down to bare rock, its air stripped away, exposed and raw beneath a star that never stops erupting. And there is the matter of the eternal day and the eternal night. Because Proxima b huddles so close to its star, the same gravity that keeps it warm has almost certainly locked it in place, so that one face stares at the star forever and the other faces away into permanent dark. Picture standing on that world. On the day side, the dim red star hangs motionless in the sky, never rising, never setting, just fixed there, endlessly, pouring its uneven light down on a baked and airless ground. Walk toward the night side, and you cross a band of eternal twilight, a ring around the whole planet where the star sits forever on the horizon, and beyond it lies a face that has never once seen its sun, frozen and black and still. There is no day and night, no seasons, no turning, no rhythm at all. Just one motionless star, one baked hemisphere, one frozen hemisphere, and the ring of dusk between them, held that way, unchanging, for as long as the planet exists. You might wonder why a small, cool, dim star like Proxima would be so violent when it puts out so little light. It seems backward that the faint ember should be the dangerous one, but it comes down to how these little stars are built. A red dwarf churns all the way through, its whole body slowly turning over like a pot of thick soup on a low flame, and that churning twists and tangles its magnetic field into knots. When those knots snap and rearrange, they release their stored energy in sudden enormous flares. A calm, layered star like our sun flares too, but gently by comparison, and its planets sit far enough away to be spared the worst. A red dwarf flares hard, and because any world warm enough for liquid water has to huddle in close, that world sits right in the blast zone, taking the full force of every eruption. The very thing that makes the planet warm enough to consider, its closeness to the star, is the thing that dooms it. Warmth and danger come from the same place, and you cannot have one without the other. And here is why this is not just Proxima's problem, but a shadow over the whole search for another Earth. Red dwarfs are, by an enormous margin, the most common kind of star in the galaxy. The great majority of stars are these small, cool, flaring embers. So when we go looking for worlds in the habitable zone of nearby stars, most of the candidates we find are exactly like Proxima b, tucked in close to a temperamental red dwarf, tidally locked, and very likely stripped and scoured. The nearest habitable world is not an unlucky exception. It may be the rule. The kind of gentle, calm, well-spaced arrangement that let our own world keep its air and its oceans for billions of years might be the rare thing, and the flare-blasted locked ember might be what most so-called Earth-like worlds actually are. Which means the disappointment at the end of this longest journey is not bad luck at one address. It may be waiting at most of the addresses we could ever reach. So the twist sharpens one more time. Not only is arrival almost impossible, and not only is the nearest destination a corpse, but the corpse is typical, and the warm blue miracle you're lying on tonight may be the true rarity in all the reachable sky. The place we are so restless to leave might be, by a wide margin, the best place there is within any distance we could ever cross. So set that beside the warm, turning blue world you're lying on right now. Here, the sun rises and sets, the air holds, the seasons turn, the whole planet spins through light and dark every day, gentle and reliable, wrapped in a blanket of atmosphere that has survived for billions of years because our star is calm. That ordinary miracle, the one you never think about, is exactly what the nearest habitable world does not have, and that is the arrival waiting at the end of the longest journey imaginable. And there is more. Because Proxima b sits so close to its star, it is very likely tidally locked, which means one side faces the star forever, and the other faces away forever. One hemisphere in permanent blistering day, the other in permanent frozen night, with no sunrise, no sunset, no turning. After billions of years of those flares tearing at it, the planet has most likely had its atmosphere stripped away, leaving not the blue and green refuge of our dreams, but a scoured, locked, radiation-blasted ember, half of it baked and half of it frozen, wrapped in the violence of a star that never stops erupting. So here is the moment I want you to feel, the heaviest one of the night. You crossed 40 trillion kilometers, you survived the impossible journey, you broke every wall, and the world you arrive at, the nearest Earth-like planet in all the universe, the best hope there is, turns out to be a corpse. A flare-scorched, airless, tidally locked rock circling a star that erupts 14,000 times brighter in 7 seconds. All that distance, all those years, all that loss, and there is nothing at the end to arrive to. The best hope in the sky, examined closely, turns out to be a place that would kill you faster than the empty crossing ever could. A world where the ground is baked on one side and frozen on the other, and the sky flares without warning into ultraviolet fire. The phrase we started with, "you never arrive," turns out to have a second flaw beneath it, one we did not see coming. It is not only that arrival keeps slipping out of reach, it is that even if you reached it, there would be nothing there worth the reaching. The light at the end of the longest journey imaginable is not a welcome. It is a flare. I do not say this to leave you in despair, and we are going to find our way to something gentler before the night is over. But we have to be honest about how far this goes, because the honesty is where the strange comfort finally comes from. We have now met 4 walls and 1 hollow destination, and there is a part of us that keeps looking for a way around all of it. A secret door, a trick, a hope the scientists have missed. So before we turn toward the quiet, let us go and check every one of those doors, one by one, and see whether any of them opens. Because the story of the ways out is, in its own way, the most revealing part of all. When a wall is this high, the mind goes looking for a door. Surely we think there is some clever way through that the ordinary calculations miss. And there are proposals, serious ones and wild ones, and it is worth walking down the row of them and trying each handle. Because what we find tells us something about the shape of the barrier itself. Start with the boldest idea in all of physics, the one that shows up whenever people talk about crossing the stars. What if you did not have to move fast through space at all? What if, instead, you moved space itself? In the year 1994, a physicist named Miguel Alcubierre wrote down a solution to Einstein's equations that describes exactly this. Imagine a bubble of ordinary flat space, with your ship sitting calmly inside it, going nowhere relative to its immediate surroundings. Now imagine space itself contracting in front of the bubble and expanding behind it. The bubble, and the ship inside it, would be carried forward, and because it is space that is moving rather than the ship, there is no speed limit. In principle, you could cross to the nearest star in days, and the crew would feel nothing, sitting still in their little pocket of calm. It is a genuinely astonishing idea, and it is real mathematics, not a daydream. But when you ask what it would take to build, the door closes. To bend space that way, the Alcubierre design requires something called negative energy, or exotic matter, a kind of stuff with properties that ordinary matter simply does not have. We have never found it in the quantities this would need, and it may not exist in any usable form at all. Worse, later work suggested that even if you could build such a bubble, the walls of it might collect deadly radiation and release it catastrophically when you tried to stop, incinerating whatever waited at your destination. So the warp bubble remains a beautiful piece of mathematics and not a path anyone knows how to walk. The door is drawn on the wall in perfect detail, and it does not open. There is a cousin of this idea that people reach for too, the wormhole, a tunnel folded through space that connects 2 distant places directly, so you could step in near Earth and step out near Proxima without crossing the space between. And it suffers from the same illness. The mathematics allows it, but holding such a tunnel open, keeping it from collapsing the instant anything tried to pass through, would again require that strange negative energy, that exotic matter we have never found and may never find, in quantities and forms that, as far as we know, do not exist in the universe. Every shortcut through space, when you chase it down to the machinery, asks for the same ingredient we do not have. It is almost as if the universe put the same lock on every door. You're welcome to imagine the tunnel, and to write down exactly how it would work, and then you are handed the bill, and the bill is always a kind of matter that reality does not seem to stock. I find something quietly honest about this, even as it disappoints. The physics is not teasing us with the solution it hides. It is showing us the same answer through every window. Go fast, and the emptiness erodes you and you cannot stop. Bend space, and you need matter that is not there. Tunnel through it, and you need the same. Wait for better technology, and the waiting never ends. Every path followed honestly leads back to the same shore, and the consistency of that is itself a kind of message. The barrier is not an accident of our current cleverness. It is woven into the structure of the thing, and the more ways you try to get around it, the more clearly you see how thoroughly it is built in. Now let us turn to the other kind of door, the ones people believe in when they would rather the problem simply were not real. There are those who say the whole thing is a lie, that the stars are not truly light years away at all, that the distances were invented and the stars are small and near. It is worth answering this gently and clearly, because the answer is one of the oldest and most beautiful measurements in science. It is called parallax, and it is nothing more than the simple geometry you use every day without noticing. Hold up a finger and look at it with one eye, then the other, and it appears to jump against the background. The nearer the finger, the bigger the jump. Astronomers do exactly this with the stars, looking at them from opposite sides of Earth's orbit around the Sun, 6 months apart, and measuring how much they shift. Back in 1838, a scientist named Friedrich Bessel used this to measure the distance to a star for the first time. Today, a spacecraft called Gaia does it for over 1 billion stars with astonishing precision, and it pins down Proxima's distance directly, from pure geometry, needing no theory of what stars are made of at all. The distance is not assumed. It is measured with a ruler made of angles, and the ruler says 4 light years and change. Then there are those who say we already have the answer hidden away, that somewhere in a secret hangar there is a working star drive, an anti-gravity craft, a way across that the public is never told about. And the trouble with this comforting story is that the same physics that forbids an easy crossing also forbids the secret. A drive powerful enough to cross the stars would carry energy signatures that could not be hidden, would demand an industrial base that could not be concealed, and would have to obey the same laws of reaction and shielding that stop everyone else. No proposed secret mechanism survives contact with the basic rules of how energy and motion work. The absence of a hidden star drive is not a cover-up. It is exactly what the physics predicts. There is no secret shortcut being kept from us, because the universe is not keeping the secret. It is simply telling everyone the same hard truth. I want to linger on that measurement of distance for a moment, the parallax, because there is something quietly heroic in it that is worth feeling. For almost all of human history, no one knew how far the stars were. They might have been lamps hung just above the clouds, or fires at an impossible remove, and there was no way to tell. People argued about it for thousands of years with no way to settle it. And then, in the early part of the 19th century, patient astronomers built instruments precise enough to catch the tiniest shift of a star against the ones behind it, as the Earth swung from one side of its orbit to the other. The shift they were measuring was unbelievably small, smaller than the width of a coin seen from kilometers away. And from that almost invisible wobble, using nothing but geometry, the kind you learn in school, they calculated the distance to a star for the first time, and found it was so large that it silenced every earlier guess. The stars were not lamps above the clouds, they were suns, unthinkably far. We have been refining that same measurement ever since, and today a single spacecraft has done it for more than 1 billion stars, mapping their distances with a precision that would have seemed like magic to those first astronomers. This is how we know that Proxima is 4.24 light-years away, and we know it not from theory, not from assumption, but from the plain, checkable geometry of watching it shift as we move. So when the distance feels too large to accept, remember that it is one of the most carefully measured facts in all of science, cross-checked a dozen ways, resting on the simplest geometry there is. The gap is not a story someone told us. It is a length we measured, with great care, over 2 centuries, and every measurement agrees. The nearest star really is that far, and knowing exactly how far, and exactly how we know, is itself one of the quiet triumphs of our kind. There is a strange comfort in that, actually. We cannot cross the distance, but we have measured it perfectly. We cannot go there, but we know precisely where there is. The reaching fails, and yet the knowing succeeds completely, and that gap between what we can know and what we can touch is, in a way, the whole story of tonight in miniature. Our minds can arrive anywhere. Our bodies can arrive almost nowhere, and learning to live gracefully in the space between those two facts may be the truest thing this nearest, unreachable star has to teach us. So we walk down the whole row of doors, the brilliant ones and the desperate ones, and we try every handle, and each one is either drawn on the wall or opens onto the same shore we started from. The warp bubble needs matter that may not exist. The faked distances are refuted by a measurement older than the light bulb. The secret drive is forbidden by the same laws that forbid the public one. There is no door, and strangely, that is where the story finally begins to soften, because once you truly accept that there is no door, you can stop clawing at the wall, and you can turn around, and you can look at what it actually means to live beside a barrier like this. That is where we are going now, into the most human part of the whole night. Let us leave the equations behind for a while and simply be with what it would feel like for people to live in a universe shaped like this. Because a barrier this strange does something to the meaning of ordinary words. It changes what it means to leave and what it means to say goodbye. Imagine a crude ship, one that somehow overcame the walls, now decades out into the dark, well and truly on its way. And imagine the moment when someone aboard sends the last message home that anyone now living on Earth will ever read in their own lifetime. Think about what that message has to cross. It travels as light, the fastest thing there is, and even so it takes years to fall back across the widening gap. By the time it arrives, the person who sent it has aged years, and the person who receives it has aged years, and the two clocks, barely separated by the small mercy of time dilation, have simply run forward, apart, in real time, on opposite ends of a distance that only grows. There is no reunion in this picture. There is no coming back within any life that overlaps. There is only the message, falling through the dark for years, toward a small blue point of light that, from out there, is already just one more star among the thousands. Picture the content of that message, and let it be ordinary, because the ordinariness is what breaks your heart. Not grand words, just the small things people say, that they are well, that they thought of home today, that they hope everyone is all right, a few plain sentences, a held breath, released into the void toward a world that will have turned many times before the words arrive. And the ones who receive it years later are reading a letter from someone who has kept living all this time, further away with every passing day, someone they will never stand beside again. The distance does not only separate 2 points in space, it separates 2 moments in time that can never be brought back into the same room. Consider, too, what the length of the crossing does to the very idea of a mission. We're used to journeys that fit inside a life, where the same person who sets out is the person who returns, changed by what they saw. But a journey of centuries has no such person. The one who decides to go is not the one who crosses the middle, and neither of them is the one who might at the very end see the star grow large. The mission outlives everyone who begins it, and everyone who carries it, and is completed, if it is completed at all, by strangers who inherited it from ancestors they never met. Think of how much trust that requires. You would be pouring your life into a purpose whose ending you will never witness, handing it forward like a lit candle to hands not yet born, believing they will carry it, and their children after them, faithfully across a gulf of time longer than any nation has ever held a single intention. We have never done anything like that. Our longest projects, the great cathedrals that took centuries to build, are the closest we have come, and even they were finished on the same ground where they began, by people who could see the walls rising. A starship crew would be building a cathedral that flies away from every hand that ever touched it, toward a spire none of them will ever see. And there is a quieter human cost folded inside the years themselves. Imagine the ordinary days aboard such a ship, tens of thousands of them, most of them with nothing outside the windows but the same unchanging dark and the same slowly shifting stars. No landfall, no new horizon, no arrival to look forward to within your lifetime. Only the long middle of a journey that began before you and will end after you. To live an entire life in transit, born in the going and dying in the going, is a shape of existence we have no real experience of and can barely imagine. It asks people to find meaning not in reaching a destination, but in the faithful carrying of the journey itself, day after day, for a purpose that belongs to a future they will never enter. That is a strange and heavy kind of courage, and it is the only kind that the honest physics of this crossing would ever allow. This is the human shape of the thing we have been calculating all night. When the crossing takes longer than a life, then to leave is to say a goodbye with no other side to it. It is not like sailing to a far country and sending letters home and one day returning with stories. It is a going that does not come back, into a silence that grows, carrying only the thin thread of light between you and everyone you ever knew, a thread that takes years to carry a single word. The horror of it, if it is horror, is not violence. Nobody is hurt, it is continuity. Everyone keeps living, on both ends, ordinary days piling up, and the only thing that happens is that the gap between them widens forever and never once closes. This is where the idea of the generation ship comes in. The great vessel that carries not a single crew, but a whole small society. People who are born, live and die aboard, so that the ones who finally reach the star are the distant descendants of the ones who left. It is a way of accepting the length of the journey instead of fighting it, of building a moving home so that arrival, whenever it comes for someone. And it is its own enormous subject, full of hard questions about what happens to people sealed inside a metal world for centuries. But even setting all of that aside, the generation ship does not escape the thing we're talking about tonight. The ones who leave still never arrive. They live their whole lives in the going, and they die in the going, and they hand the journey to children who will also never arrive, and so on for generations, until finally, maybe, some distant descendant sees the star grow large. Everyone in between spends an entire existence travelling toward a place they will never reach. The ship is a way of arriving eventually for someone, by asking everyone else to spend their lives never arriving. And that reframes the whole thing in a way I want you to feel before we turn toward the end. Because if the only way to truly reach the nearest star is to give up on any single person arriving, and to think instead in terms of generations and centuries, and the slow patience of a whole civilization, then arrival stops being something a traveller does and becomes something a species does, across time, the way a cathedral gets built by people who will never see it finished. The individual never arrives. The individual was never going to. The question quietly changes from whether you can reach the star to whether your kind can keep reaching, across spans of time longer than any life, without ever once getting to stand at the end of it. That is a different kind of journey, and it asks a different kind of courage, and it is, I think, the truest shape of what going to the stars would actually mean. And yet, sitting with this, something shifts. Because if you truly accept that the bodies cannot make the crossing and come back, you start to ask a different question. What can make the crossing? And the answer is already in your hands. Light can. Messages can. Not people, not in any life we know how to live, but knowledge, patience, attention. A civilization that accepts it will never arrive, as travellers can still reach toward the nearest star in the only way that works. It can send its instruments and its questions ahead of its bodies. It can photograph instead of land. It can learn to think in centuries and in messages rather than in journeys and in returns. The same sentence that trapped us on the launch pad, wait for the better ship, turns out to describe not only a trap but a kind of patience. A species slowly learning to reach across a gulf it cannot personally cross, the way a parent reaches toward a future they will not live to see. Think about what we have already sent in that spirit without ever leaving home. We have sent our little robots to the edge of the solar system, still faintly calling back to us after decades. We have pointed our finest telescopes at Proxima and its planet, and pulled real knowledge out of a point of light we can barely see. We have measured the mass of a world 4 light-years away, and the flares of its star, and the shape of its orbit, all without a single traveller setting out. In a real sense, we have already reached the nearest star, not with our bodies but with our attention, and it turns out that attention crosses distances that flesh never can. Light comes to us freely from Proxima every night, 4 years old by the time it arrives, and in that light is written almost everything we know about the place. We do not have to go. The star, in a way, comes to us, and always has. And maybe that is the shape of reaching that actually fits a universe built like this one. Not the bold crossing and the triumphant landing, but the patient listening, the careful looking, the long slow accumulation of understanding sent back and forth across gulfs no body can span. It is a quieter kind of exploration than the one our stories trained us to want. There are no footprints in it, no flags, no coming home to cheering crowds. But it is real, and it works, and it is happening right now tonight, as instruments we built turn their patient faces toward that dim red star and gather what it freely gives. We are already reaching. We simply had to learn that reaching and arriving were never the same thing, and that the first one was always the one that mattered. So we come, gently, to the edge of understanding all of it. We have met the 4 walls and the hollow world and the closed doors and the long goodbye. And now, at last, we can say plainly the thing the whole night has been circling, the answer to the question we posed at the very beginning. Why is the journey to the nearest star scarier than you think? And why, in the truest sense, do you never arrive? Let us put it into words, clearly and slowly, now that we have earned it. Here is the answer, plainly, now that we have walked the whole way to it. You never arrive at the nearest star, and here is exactly why. It is not one reason. It is 4 standing one behind the other, and only the first of them is the one everybody talks about. The first reason is distance, and the speed you cannot beat. The star is just over 4 light-years away, which is 40 trillion kilometers, and the fastest thing we have ever built would take 73,000 years to get there, while the fastest thing we can seriously imagine would still take decades and carry nothing but a camera. Light itself, the absolute limit, takes more than 4 years, and everything we can make is far slower than light. That is the wall everyone sees, and if it stood alone we could still dream of climbing it someday. But it does not stand alone. The second reason is that the crossing itself destroys the traveller. The empty space between the stars, so peaceful when you are still, becomes at high speed a continuous sleet of atoms carrying nuclear energies, and a rain of dust grains each striking with the force of bombs, and a bath of radiation that no shielding light enough to carry can hold back across decades. To go fast enough to make the trip in a lifetime is to be eroded steadily for the entire length of it. The speed that shortens the journey is the same speed that takes you apart. The third reason is that even a fast ship cannot stop. Slowing down is as hard as speeding up, and the fast designs carry no brakes, so they reach the star and tear straight through it in an afternoon and fall out the far side into the further dark. They can reach the nearest star. They cannot arrive there. The physics keeps swapping the word we want, arrive, for the word it allows, pass. And the fourth reason is the strangest, the one that lives not in space but in the mind. Because our speed keeps slowly improving, a ship launched later and faster will always overtake a ship launched now, which means the smart thing, the rational thing, the thing that actually gets a traveller to the star soonest, is to wait for the better ship. And that reasoning never expires. Every generation runs the same honest calculation and reaches the same honest answer, not yet. And the launch that makes sense to begin is always the one you begin later, and later never comes. We are held home not by an enemy, but by our own good judgment, which never once makes a mistake and never once lets us go. And there was that fifth thing, underneath the 4 walls, the one that waited at the end of the road. Even if you somehow beat all 4, even if you crossed the distance and survived the erosion and solved the stopping and escaped the weight, the world you would arrive at is not a refuge. It is a locked, airless, flare-scorched ember circling a star that erupts 14,000 times brighter in 7 seconds and pours 400 times Earth's X-rays across a surface that never turns. So the phrase we began with turns out to have a flaw beneath its flaw. You never arrive, and even in the impossible case where you did, there would be nothing there to arrive to. The reaching and the destination fail together from opposite ends. I want to be careful here, because it would be easy to hear all of this as a counsel of despair, as though the lesson were simply that we are trapped and small and should stop dreaming. That is not the lesson, and it is not what the physics says. The physics does not say the stars are worthless, or that wonder is foolish. It says something more precise and in its way more interesting. It says that arrival, the particular act of a living body crossing to another star and standing on a world there and coming home to tell about it, is not the shape the universe allows. The universe allows looking, it allows measuring, it allows sending light and questions and machines, it allows a civilization to reach, patiently, across time. It simply does not allow the one thing our stories always end on, the arrival, the landing, the return. And once you stop demanding that particular ending, the whole picture changes from a prison into something closer to a horizon, which is where we're about to end. Now look at those 4 reasons together, and see the thing I most want you to carry away from tonight. Only the first of them, distance, is about how far the star is. The other 3 are not about distance at all. The erosion of the crossing, the impossibility of stopping, the trap of the weight, these would haunt us even if the star were nearer. They are not features of Proxima. They are features of what it means to move a living thing across an interstellar gulf and bring it to rest at the far end, in a universe with a speed limit and a body that ages and a mind that must decide when to leave. That is why the journey is scarier than you think. Because you think the problem is that the star is far, and the truth is that the distance is the shallowest of 4 barriers, 3 of which have nothing to do with how many light years lie between us and the nearest light. That is why you never arrive. Not because you cannot cover the distance, though you very nearly cannot, but because arrival, real arrival, the stopping and the staying, keeps dissolving into something else at every level you examine it. It becomes a flyby or a wait or a goodbye or a corpse of a world at the end. The nearest star stays, in the simplest sense, 4 years of light away. And in every sense that matters to a traveller with a heartbeat, it moves further off the harder you reach for it. It is not a place you go. It is a direction you fall toward, forever, without arriving. Let me give you one image to hold all 4 of these together, because 4 walls is a lot to carry, and an image travels better than a list. Think of trying to reach the horizon on a long, flat plane. You can walk toward it all day. You can run. You can ride the fastest horse. And the horizon never comes closer, because it is not a place on the ground. It is a relationship between where you are and how far you can see. The nearest star is a little like that, except that the horizon of arrival recedes for 4 separate reasons at once. It is too far to reach in a life. The path there wears you away as you walk it. You cannot stop even if you get there. And the wisest moment to set out is always a little further into the future. 4 different reasons, and every one of them pushes the horizon of arrival back exactly as you reach for it. That is why it is not a distance you can close, it is a horizon you can only face. And I think there is something important in the fact that it took us the whole night to see this clearly. If you had asked at the start why we have not gone to the stars, the easy answer, the one almost everyone gives, is that they are too far. And that answer is not wrong, but it is shallow, and it hides the more unsettling truth underneath, which is that even if they were closer, we still could not truly arrive because 3 of the 4 barriers were never about distance at all. The farness of the star is the part we can see and point to and complain about. The real reasons you never arrive are quieter and stranger, folded into the nature of speed and matter and time and choice, and you only find them by walking the whole way to the edge, as we have tonight, and looking over. And notice, now that we are here, how the word arrive has quietly changed its meaning over the course of the night. When we began, arrive meant something simple and hopeful. It meant getting there, standing on the far world, planting the flag, sending word home, coming back with the story. But wall by wall, the physics took that meaning apart. Getting there became a flyby you cannot stop. Standing on the world became landing on a scoured, locked ember. Coming home became a return that no life is long enough to make. Sending word became a message that takes years to fall across a gap that only widens. Every piece of what we meant by arrive turned out to be closed to us, one after another, until the word itself hollowed out. That is the real answer to why you never arrive. It is not only that the star is hard to reach, it is that arrival, examined closely, dissolves into a set of things none of which the universe will let a living traveller have. So let the phrase stand plainly as the truth of the whole night. You never arrive, not because we are not clever enough, though the walls are high, but because arrival, real arrival, is not a shape the universe permits across these distances, for creatures like us, with bodies that age and clocks that barely bend and minds that must choose when to leave. The nearest star will let us look. It will let us measure and wonder and reach with everything except our own 2 hands. It will not let us arrive, and having walked all the way here to see that clearly, we can finally turn back towards something gentler and ask what it might mean to make peace with a sky built this way. And here, right at the bottom of the whole story, something unexpected happens. Because once you truly understand that you never arrive, once you stop struggling against it and simply let it be true, the fear starts to change into something else. It starts to turn into a kind of understanding about where we actually are and what this nearest, unreachable light has been showing us all along. Let us end there, in the quiet, with the gentlest and largest thought of the night. We have spent this whole night learning why you never arrive at the nearest star, and I want to end not in dread but in something calmer and wider, because there is a gift folded inside this barrier, and it only shows itself once you have stopped trying to break through. Think about what the nearest star has actually done for us, simply by being unreachable. All through this journey, it has been teaching us the true size of the room we live in. Every wall we met was really a lesson in scale. The 73,000-year crossing taught us how large a single step out of our solar system truly is. The sleet between the stars taught us that even the emptiness is emptier than we imagined. The weight calculation taught us that our own cleverness, which feels so powerful, advances slowly against a gap this size. And the flare-scorched world at the end taught us how rare and how gentle our own warm, turning blue home really is, circling its steady yellow star wrapped in air, spinning through day and night, quietly holding us the way almost nowhere else in reach ever could. There is a way of looking up at the night sky that changes once you truly understand this, and I hope you carry it out of tonight with you. Most of us, when we look at the stars, feel a small pull of longing, a sense that they are places we might one day visit, waiting for us, patient destinations scattered across the dark. And there is beauty in that longing, but there is a truer and, I think, a gentler way to see them. The stars are not waiting for us. They are showing us where we are. Each point of light is a marker of a distance we cannot personally cross, and together they draw, more clearly than anything else could, the exact size and shape of the small warm country we actually inhabit. To look up is not to see a set of doors we have failed to open. It is to see the walls of the only room that was ever truly ours, lit up and beautiful, defining the space in which our whole existence happens. And notice what that does to the way you might feel about being here, tonight, in this one place. If the nearest star is unreachable, then this world, this single turning planet, is not a way station we are impatient to leave. It is the destination. It is the arrival. We are already, right now, standing on the one world in all the reachable cosmos that holds us gently, and everything we will ever truly touch is here. That is not a smallness to mourn. It is a home to be astonished by. The unreachability of everywhere else is exactly what makes this place the whole of what we have, and there is a kind of peace in accepting that, in setting down the longing to be elsewhere and simply being, fully, where we already are. The nearest star is not, it turns out, a door we fail to walk through. It is a horizon, and a horizon does something a door cannot. A horizon shows you where you are. It marks the edge of the country you actually live in, and the country we actually live in is this one, this solar system, this pale blue world, and the nearest star, by refusing to let us arrive, has drawn the boundary of home more clearly than anything else could. It has told us, in the plainest terms the universe has, that we are here, and that here is precious, and that here is, for now and perhaps for a very long time, all of the cosmos we can truly touch. And there is a quieter dignity in the reaching itself, even knowing we never arrive. Because a species that accepts it cannot personally cross this gulf does not have to stop reaching. It learns to send light instead of bodies, to ask questions it will not live to have answered, to point its finest instruments at that dim red ember and photograph a world it will never stand on. The same sentence that trapped us on the launch pad, wait for the better ship, becomes, on the far side of understanding, not only a trap but a description of patience, of a small warm species learning to reach across a distance too great for any single life, the way you might plant a tree whose shade you will never sit in. There is something almost tender in that. We keep looking. We keep measuring. We keep pointing ourselves in that direction, toward the nearest light, knowing full well what the walls are, and we do it anyway, because the looking is its own kind of arriving. I keep coming back as this night winds down, to how gently all of this can be held once you stop fighting it. There is a version of this story that is only sad, that ends with us trapped and small and going nowhere, and if you stop early that is the version you get. But if you follow it all the way to the end, past the four walls and the flare-scorched world and the closed doors, you come out somewhere unexpectedly peaceful. Because the same facts that say you can never leave also say that here, where you already are, is the one place in all the reachable universe that holds you. The walls that keep us in are the same walls that make this home so rare and so precious. You cannot have the second truth without the first. The unreachability of the stars is exactly what makes the ground beneath you the whole and entire miracle that it is, and so the nearest star becomes, in the end, not a rebuke, but a teacher. It stands out there, 4 light years off, patient and beautiful and forever just out of reach, and simply by being unreachable it tells us, every clear night, the truth about where we live and how rare it is, and how much of the cosmos we will only ever touch with our minds and our instruments and our longing. That is not nothing. That may in fact be the most a small warm species could ever ask of the sky, that it teach us the size of our home and the worth of it, and that it give us forever a direction to wander toward. We were never going to arrive, but we were always going to look, and the looking has already carried us further than our bodies ever could. So let the nearest star hang there tonight, just over 4 light years away, exactly where it has always been, unreachable and close, the first light outside our own, and the one we can never touch. Let it be a direction rather than a destination, and let that be in the end a comfort rather than a grief, because a direction you can hold forever. A direction does not disappoint you the way a destination can. It simply orients you, quietly, night after night, towards something larger than yourself, while you remain safe and warm in the one small place in all the cosmos that was ever truly arranged to hold you. You never arrive, but you are never really meant to go. You are meant to look up and to wonder and to learn the size of your own home by measuring the distance to the next one, and that in the truest sense, is a kind of arriving after all. Rest now, here, in the only place there is. The nearest star will keep its light burning out there in the dark, patient and far and beautiful, and it will still be there tomorrow and the night after, pointing the way, asking nothing of you but that you close your eyes and let yourself drift, held gently by the small warm world that never once asked you to leave.